Everyone, today we are going to discuss about energy stored in a capacitor. Yesterday we discussed about the value of capacitance of a parallel plate capacitor. Now whenever a capacitor, say parallel plate capacitor, which is denoted like two parallel lines of same length, is connected with a battery, it gets charged. It gets charged equal to the voltage of the battery. So say after fully charged, the charge on the capacitor is plus Q and minus Q. So as it is charged, some electrical energy is stored in the capacitor. Okay, we are going to find out the derivation and the expression of the energy stored. Now for that, simply consider a parallel plate capacitor. So initially the plates have no charge. Now suppose we transfer charge from positive charge from this plate to this plate. So this plate will get positively charged and this plate will get negatively charged. And with this process we will make it plus Q and minus Q at the final stage. Now suppose at any intermediate state, this has a charge Q prime and this has a charge minus Q prime. Okay. Now the direction of the electric field inside the capacitor is in this direction. So to move more charges from this plate to this plate, we will have to do an additional work done. Now suppose at this point we want to move a small positive charge dq prime from plate, say this is B, to plate A. So we have to do a work done. Now at this point, if the potential difference between the plate is V prime, we can write V prime as V prime equals to Q prime by C, where C is the capacitance of this capacitor. Now one thing to remember, the capacitance of the capacitor is independent of potential or charge in these plates. Okay, so at this moment when it has charge Q prime and it is minus Q prime, the potential difference between the plates will be this one. And now if you want to move this little charge from plate B to A, we have to do a work done. That work done we can write as dW equals to, as formula you know, W equals to VQ. So this one is V prime into dQ prime. So if we put the value of V prime, we can write Q prime by C dQ prime. So this is the work done to move small amount of charge dQ prime. Now initially the plates or the capacitor had no charge, and suppose at the final time when it is fully charged, the positive plate has plus Q charge and the negative have minus Q charge. So actually we are charging it from charge 0 to Q. So the total work done to charge it to the charge Q will be W equals to integration dW integration Q prime by C dQ prime. The limit will be 0 to Q. Now if you integrate it, capacitance is constant, so it will come out of the integration. So 0 to Q prime dQ prime. Integration of Q prime is Q prime square by 2. So 1 by C Q prime square by 2, limit 0 to Q. So first we will put the Q, then we will put the 0. So by that we will get Q square by 2C. Now when it is fully charged, say it has charge Q and the potential difference between the plates is now V. So now this is the PD. So now we can write Q equals to CV. So first substituting the value of Q, we will get one equation is first It is already we have derived q square by 2c. Substituting the value of q equals to cv, we will get half cv square, or substituting the value of c, we will get half vq. So this is the energy stored in a capacitor in terms of its capacitance and potential difference, in terms of charge and its capacitance, and in terms of charge and its potential difference. Now this work done is stored in the capacitor as potential energy. So you can also write it U equals to. Now it is possible to see the potential energy stored in the capacitor in electric field. For that, simply consider a parallel plate capacitor, right? Now for a parallel plate capacitor, the value of capacitance is epsilon naught A by D when there is no dielectric medium, and if the potential difference between the plates is V, we can write electric field as equal to, taking the magnitude, equals to V by D. Now we will put these values in potential energy equation. You can take any of the equations. Let me take half CV square. So this is the energy stored in a parallel plate capacitor. Just putting the values of C as epsilon naught A by D, and in case of V it is E multiplied by D, so this is E square D square. So just rearranging a little bit, half epsilon naught A square into AD. Now here if you see AD, if the plate has surface area A and the separation is D, AD actually gives you the volume inside the capacitor. So we can actually say the electric field is inside the capacitor. So this much amount of energy is stored inside the capacitor. So the energy per unit volume or energy density can be written as capital U by AD, which is denoted as small u, is half epsilon naught E square. So this is energy density. Now here we have find out this energy is related to electric field. We find it out for parallel plate capacitor, but it is actually true for electric field in case of any type of configuration. So if there is electric field E, due to any configuration, the energy density of the electric field will be half epsilon 0 E square. Now this derivation is important for your exam purpose. Also generally the questions asked energy stored in a capacitor, they generally give you a circuit consisting of few capacitors and you have to find the energy stored in it. For that we need to find out how to calculate the equivalent capacitance. So let's start with that. Now any combination of capacitors is actually a mix of series combination and parallel combination. So let us first start with series combination. So take two capacitors having capacitances C1 and C2 are connected in series, say with a battery V. Now once you connect the capacitors with a battery like this, the capacitors will start accumulating charges, and at the steady state both of the capacitors will have same charge. So say this plate is plus Q, this will be minus Q, and this is plus Q, this is minus Q. So in simple words, both the capacitors will have the same charge when they are connected in series. And suppose the potential difference across this capacitor is V1 and that same for this capacitor is V2. So for this capacitor we can write V1 equals to Q by C1, and for the second capacitor we can write V2 equals to Q by C2. Now equivalent capacitance means if we replace these two capacitors by a single capacitor, the potential difference and the charge will remain same. So that means if we replace it say by a single capacitor having capacitance C S, connect with a battery V, it should have charge Q. Now from this you can write V as sum of the potential differences as they are connected in series. So you can write V equals to V1 plus V2, and here you can write V equals to Q by Cs. So comparing these two equations, first put these values, Q by C1 plus Q by C2. So comparing these two equations, you can write Q by Cs equals to Q by C1 plus Q by C2, or Q will cancel out. 1 by Cs equals to 1 by C1 by 1 by C2. So this is the equivalent capacitance of capacitors in series. Now there can be more than two capacitors. So in that case we can write just as, suppose there is n number of capacitors, C1 plus C2 so on 1 by C in general. Now let us consider parallel combination of capacitors. Say two capacitors having capacitances C1 and C2 are connected in parallel with a battery. Okay, parallel means the terminal of the capacitances will be collected like this. Now here, since they are parallel, both will have a voltage V, potential difference V, but the charges will be different. So say this one has a capacitance charge Q1 and this one has a capacitance Q2. So for the first capacitor we can write Q1 equals to C1V, and for the second one you can write Q2 equals to C2V. Now equivalent of these two capacitor means we will have a capacitor Cp such that its potential difference is V and the total charge on this one is Q equals to Q1 plus Q2. So for this case we can write Q equals to CPV, and here the total charge is what, Q1 plus Q2 equals to C1V plus C2V. So just compare these two equations and we will get CPV equals to C1V plus C2V, or Cp equals to C1 plus C2. So for n number of capacitances we can write Cp equals to Cp equals to C1 plus C2 to Cn. So this is parallel combination of capacitance. Now let us solve a numerical. So let us consider a circuit like this, 4 capacitors C1, C2, C3, C4, all of them have same values, 10 microfarad, are connected like this with a battery of 500 volt. Now what we have to find? We have to find the equivalence capacitance of the system. So C equivalent we have to find, and charge on each capacitor, that we have to find Q, and also you have to find the total energy stored in this system. So we have 3 things to find. Okay, for that first we have to find the equivalence capacitance. To find that we have to understand which are the capacitors are in series and which are in parallel. Okay, now for this just simply assume that these are like wires, and suppose this is 500 volt, and if these are only wires, so like current would come in this direction, and from this point the current would divide like this. This current would go like this current would go and they would join here and come like this. Okay, though in steady state there is no current, but just assume it like that. So if you see, if there was any current, these three would, from these two capacitors there would be same value, because they are in, because this current has no other place to go. So C1, C2, C3 are in series. So if we modify this, say C1, the series combination of C1, C2, C3 is CS. If you modify the circuit, this will become Now we will only draw 1 instead of 3. So this is your CS, and here it is your C4, and here is the battery. So this is your CS, this is your C4, and here is the battery 500. So now you can easily see the terminal of CS and C4 are same. They are connected in this point. Since there is nothing, so this is just wire. So this point and this point will have same potential, and this point and this point is so on. So CS and C4 are in parallel combination. So C1, C2, C3 are in series. This combination is CS. With that, C4 is parallel combination. So let us first find out CS. So since C1, C2 and C3 are in series combination, we can write 1 by CS equals to 1 by C1 plus 1 by C2 plus 1 by C3. They all have 10 microfarads value. So we'll just put it 1 by CS equals to 1 by 10 plus 1 by 10 plus 1 by 10. Calculating, we will get 10 by 3 microfarad. So CS is 10 by 3 microfarad and C4 is also 10 microfarad. Now they are in parallel, so their combination, that means the total capacitance, the circuit C equivalent equals to, they're in parallel, so they will just add up C4. So that is 10 by 3 plus 10. So this is like 3.33 and this is 10, so this will be like 13.3 microfarad. So this is the equivalence capacitance of this circuit. Now you have to find charge on each capacitors. Now since C1, C2, C3 are in series combination, they will have same charge. Okay, C4 will be different, maybe different, but C1, C2, C3 will be same charge as CS. Now CS and C4 are in parallel, so the potential difference across CS is 500, same for C4. So if we apply for CS, we can write charge on CS, say QS equals to CS into V. So this will be the charge on CS. Now since CS is equivalent of these three, C1, C2 and C3, which are in series, so same amount of charge will be stored in C1, C2 and C3. So CS value is 10 by 3, 10 by 3, convert it into farad from microfarad, 10 to the power minus 6, V is 500. And calculating, it will give you 1.7 into 10 to the power minus 3 coulomb. So you can write Q1 equals to Q2 equals to Q3. All three are in series, have the same charges, which is this one. Now similarly for C4, you can find out Q4 equals to C4 into Q equals to C 500. C4 is 10 into 10 to the power minus 6 into 500, or multiplying we will get 5 into 10 to the power minus 3 coulomb. So we have calculated already equivalent capacitance and charge on each capacitor. Now you have to find the total energy stored in the system. Total energy stored is, say, half CV square, where C is equivalent capacitance and V is this battery 500 volt. This battery 500 volt. So C equivalent is 13.3. So just put the value 13.3 into 10 to the power minus 6, and V square is 500 into 500. And calculating, you will get 0.30 approximately. So this is how they will give you a system of capacitors, and you will have to find these kind of things. So we'll solve more numericals now on Google Classroom.